Can you make it across the finish line when every step depends on your last? Jump Game is a Pattern Mastery 100 favorite and a classic at Google, Facebook, and Amazon, testing your greedy algorithms and array reasoning. 30% of candidates trip over edge cases or inefficient DP. Master this, and you'll breeze through reachability and greedy interview problems. Let's solve Jump Game using the basic approach, your step-by-step strategy for any reachability or greedy challenge. Given an array of non-negative integers, where each element represents your maximum jump length from that position, determine if you can reach the last index. List of integers nums, max jump at each index. Boolean. True if you can reach the end, else false. Picture crossing stepping stones in a river, where each stone tells you how far you can jump ahead. Interviewers might ask, how would you check if a player can always reach the end in a game with varying step sizes? What's tricky? DP is possible but unnecessary. Greedy works better. Watch out for zeros in the array, they can block progress if you can't jump past them. Must always keep track of the farthest reachable index. Initialize a variable farthest to 0. Iterate through the array. If the current index is greater than farthest, you're stuck, return false. At each index, update farthest equals max farthest, I plus nums I. If farthest ever reaches or exceeds the last index, return true. Initialize farthest equals 0. Loop over nums with index I. If I greater than farthest, return false. Update farthest equals max farthest, I plus nums I. If farthest greater than equals len nums, 1. Return true. If loop ends, return false. Solution 1. Greedy, furthest reach, time complexity. ON. We begin by defining a class called solution. This just gives us a clean place to store our method. This defines our function canJump, which determines whether we can reach the last index of a list by jumping forward using the rules given in the problem. We set reachable to 0. This variable represents the furthest index we can currently reach. Think of it like the maximum distance your character can jump so far. We store the length of the array in n, which tells us how many positions exist in total. We loop through the array from index 0 to index n-1. This loop runs n times on. We check if our current position I is beyond what we can reach. If we've ever landed on an index that we cannot physically jump to, then we're stuck. So if we're standing at an unreachable index, the answer is false, we cannot reach the end. Otherwise, we update our furthest reach. I plus nums I represents how far we can jump from this position. We compare it with our current reachable distance and keep the maximum. This is the greedy step, always track the best possible reach. We check if our furthest reach has already reached, or passed, the last index. If yes, we don't need to continue, we know we can win. So if we can reach the last index at any point, we immediately return true. And if we finish the loop without getting stuck, that means we can always reach the end, so we return true. Final wrap-up. And that's how this algorithm works. It first tracks the furthest index we can reach, then walks through the array, updating that reach until either we get stuck or reach the end. Efficient, simple, and elegant. Test case check, jump game using greedy reachability. Let's test our function using this input. 2, 3, 1, 1, 4. These numbers represent how far you can jump from each position. And our goal is to determine whether we can reach the last index. Here's why the solution works. We track the farthest position we can reach as we move through the array. If at any point our current index goes beyond this reachable range, we know we're stuck. Otherwise, we keep expanding the reach by taking the maximum of the current reachable distance, and the new jump range from the current index, I plus nums I. And that's exactly what our program outputs. True. The result matches the expected value, confirming that the greedy reachability method is working perfectly. Wrap up. So, our implementation is correct. The algorithm successfully checks whether we can reach the final index by tracking the maximum reachable position. Efficient, accurate, and reliable. Solution 2. BFS traversal time complexity. ON squared, worst case. We import deck, a fast double-ended queue. This structure allows us to pop from the front efficiently. Perfect for BFS, breadth first search. We define a class called solution to neatly hold our method. This defines our function canJump, which determines whether we can reach the last index of the array using BFS exploration. We store the length of the input list in n. This tells us how many positions exist. We create a set called visited containing index 0. This ensures we don't revisit the same index twice, preventing infinite loops and reducing extra work. We initialize a queue for BFS and start by adding index 0. This means our BFS exploration begins at the very first position. We begin a BFS loop. As long as there are positions left to explore, the loop continues. This BFS may explore up to n² positions in the worst case if every index can jump many steps. We remove the next position from the front of the queue. This is the current index we will explore. We check if this index is the last one in the array, the finish line. If we reach the last index, we've succeeded. We can jump to the end, so we return true immediately. We try all possible jump lengths from this position, from 1 up to the maximum allowed by num's I. This inner loop is where the worst case n² behavior comes from. We calculate the next index we'd land on after taking this specific jump. We only consider this next index if it's inside the array bounds and we haven't visited it before. This prevents wasting time revisiting old positions. We mark the new index as visited so we don't process it again later. And we add this new index to the BFS queue so we can explore its possible jumps next. If we exit the BFS loop without ever reaching the last index, that means there's no valid path to the end. So we return false. Final wrap-up. And that's how this algorithm works. It first sets up a BFS queue and tracks visited positions, then explores every possible jump from each reachable index until either we reach the end or run out of options. Efficient, simple, and elegant. Test case check, jump game using BFS search. Let's test our function using this input. 3, 2, 1, 0, 4. These numbers represent how far you can jump from each index, and our goal is to see whether we can reach the last position in the array. Here's why the solution works. We treat each index like a node and perform a BFS search. Starting from index 0, we explore every reachable next position using all valid jump distances. We also track a visited set so we never recheck the same index. And that's exactly what our program outputs, false. This matches the expected value, confirming that our BFS exploration correctly detects when the last index cannot be reached. Wrap up. So, our implementation is correct. The algorithm successfully checks all reachable paths using BFS and accurately identifies when the end cannot be reached. Efficient, accurate, and reliable. Jump game. Let's do a recap. So, we've just tackled one of the most popular reachability problems in interviews, jump game. It's fast-paced, logical, and a great way to show that you understand how to balance dynamic programming ideas with greedy reasoning. Once you grasp this, you'll spot the same pattern in dozens of real-world and interview problems. Breakdown recap. At its core, the problem asks, can you reach the end of an array if each element tells you how far you can jump? It's like stepping across stones. Every number tells you how many stones ahead you can move, and your goal is to make it to the last one without getting stuck. Assess recap. We compared two approaches, dynamic programming and greedy. While DP works, it's unnecessary here. Greedy logic is more efficient. The key insight was simple. Keep track of the farthest point you can reach. If at any point your current index goes beyond that limit, you're stuck. Otherwise, you keep pushing that boundary forward. Structure recap. We structured it around one core loop, moving through the array while tracking the farthest reachable index. If the current position is ever out of reach, we stop. If we extend the farthest reach to or beyond the final index, we've made it. It's clean, linear, and effective. Implement recap. We ran the greedy logic step by step on LeetCode. The code executed perfectly, no runtime errors, no boundary issues, confirming that the logic holds even with tricky cases like zeros and single-element arrays. Check recap. All test cases passed. The algorithm successfully determined when the end was reachable, and when it wasn't. It handled small, large, and edge cases exactly as expected. Efficient, reliable, and consistent. Closing insight. The key takeaway? Jump game teaches you how to think ahead, literally. It's not about every step, but how far you can go from each one. Mastering this greedy mindset will help you tackle a whole class of problems built around reachability, optimization, and forward-thinking logic.